Today I will be presenting our study on privacy threats that exist in fitness tracking social network. So fitness tracking or self-tracking market is booming right now. It's generating billions of dollars of revenue per year, and its market is supposed to reach 48 billion by the year 2023. This market growth is partially led by increasing use of self-tracking or fitness tracking services or applications. These where a lot of these applications surfaced in the last decade, including Strava, Garmin Connect, and MapMyTrack. Essentially, all these applications provides you with the same functionality, where the user or the athlete can map or track their activities such as riding or running. Then later they can analyze their activity, such as finding the average pace, heart rate, or duration. Finally, they can share their activity with the public and can compete in challenges. However, sharing data in social network, sharing data has an intrinsic risk. And in this case, people usually run from their sensitive locations, such as home or offices, and broadcasting these routes to the public can have privacy concerns. As we have seen in the news that bicycle thieves are targeting users of this application to target and steal expensive bikes and equipment. Similarly, we saw a global heat map incident where Strava uploaded public activities in aggregate in a form of a heat map, which is useful for planning, transit planning, or finding popular routes, but it leaked very sensitive location information, such as classified military addresses, classified military bases, or intelligence agencies. So in order to tackle these problems, these services provide you with various privacy features. One of the features is Endpoint Privacy Zone. In order to understand the Endpoint Privacy Zone feature, let's take a sample running activity. This running activity happened during USENIX Security 2016 in Austin. The route of this running activity is shown in red on the map. This activity started from the conference hotel and ended at the conference hotel. Now, if the user wants to hide the endpoints of this activity, they can use this feature of Endpoint Privacy Zone, which is essentially a circular zone centered at the private or protected sensitive address, and any portion of the activity that lies inside circular zone hides from the public. For example, in this case, let's give the address of the conference hotel as our sensitive location and specify the radius of the circular zone that we want. Once this circular zone has been deployed, the other people will see the route as shown on the slide. Now some part of the route has been removed for the public. Now you might have imagined like what happened in the background. Strava, once you specified your protected or sensitive location address, Strava created a circular zone centered at that address and simply removed any part of the route that lied in that circular zone. Well, but do you see any problem with this? Well, you can identify the center, which was the sensitive location, by simple geometry. Let's say I give you two points and I tell you the radius. You can easily draw the circle and tell me the center. But since these applications provide you with the various radii, and you can make multiple guesses. In this case, if the service provides you with 3 radii, you can make 3 circles. But as soon as you get 3 or more points, you can narrow down your search space and you can get 1 EPZ or 1 center. So now the question is it that simple? Can you simply just apply this geometry and find the EPZ? Well, the answer is no, definitely no. There are a lot of factors that contribute in finding this EPZ not that easily. The first one is that there are multiple endpoints, and which endpoints are actually associated with the EPZ, it's unpredictable. So when you take this point and try to predict, you can have multiple EPZ, while on only one EPZ was the correct one. The next one is the GPS sampling error. So there could be jitter in the GPS points that you get from these activities, and due to that, the points may not exactly lie on the circle. And when you try to redraw the circle, you can get wildly inaccurate results. So once we found out that there is a problem with this, we set out to systematically evaluate this privacy feature and try to determine whether or not the trust of users of this feature is misplaced. So we started by collecting a data set, activity data set from an exemplar fitness tracking service. In this case, it was Strava.com. Then we designed our own searching algorithm, which we validated and evaluated through the data set we collected before. And then finally, we proposed some mitigation strategies to solve this EPZ searching, EPZ feature. So in order to get this data set, we scraped 1 month of activity data set from Strava.com. For each activity, we collected GPS coordinates, activity types, duration, and any other metadata that we thought will be useful for us. In total, we collected 21 million activities with various activity types. And this 21 million activity consisted of 18.5 million non-EPZ activities or the unprotected activities, 2.3 million EPZ activities, the activities that were using EPZ, consisted of 3 million different athletes, and these activities from all over the world. So once we got this data set from Strava.com, we tried to get our algorithm for EPZ searching, circle searching. So before devising our own algorithm, we looked into the existing solution. In particular, we looked into least square circle filled algorithm. But we quickly find out that this algorithm does not meet our needs because of several reasons. The first one is that it considers all the endpoints. As I mentioned before, that the endpoint that belongs to the EPZ is unpredictable. You cannot tell which one belongs to the EPZ. And if you give a wrong endpoint to this algorithm, it will give you wildly inaccurate results. The second one is that it will consider all the radii, all the possible radii, while we know that these services only allow you some finite number of radii. Third, it does not cater any GPS coordinate inaccuracies. And finally, it has a large runtime complexity. So once we found out that this is not working, we moved on proposing our own EPZ searching algorithm. So at a very high level, this algorithm works in 4 steps. First, in the first step, it will generate candidate EPZ. In order to generate candidate EPZ, all possible candidate EPZs, it will take each pair of activities, and for each pair of activity, it will get all possible combinations of the endpoints. And using these endpoints, it plugs those endpoints in the simultaneous equation of the circle and solve this for each possible radii for that particular service. Each solution of this simultaneous equation will give you one candidate EPZ. Once this process has been finished and we got all the candidate EPZ, we moved on to the next step, where we try to use a consensus-based procedure to assign confidence score to each EPZ, where confidence score means that how many different activities independently agree on the location of this EPZ. So if a lot of activities agree on the same EPZ, that EPZ will have a higher confidence score. Once we assign the confidence score, we move on to solve this jitter problem in the GPS coordinates. So we use a parameterized threshold. Essentially, what a threshold allows you is that two EPZ, if the distance between two EPZ is less than this threshold, they are considered the same. Next, we filter out any candidate EPZs which do not make sense. For example, if the candidate EPZ intersects with other portion of any other route, or if the candidate EPZ have a confidence score less than some threshold. So once we got all the EPZs, we finally predict one EPZ which has the highest confidence score. Note that we use a training run phase to find best possible threshold for each service. So once we got our algorithm, we moved on validating our algorithm. So what we did was we took all the activities that weren't using EPZ, and then we synthetically created our own EPZ, just like the Strava does. And in this case, as we knew the ground truth, we tried to predict using our own algorithm the sensitive location or the circle center. Our results showed that we could identify 97% of the athletes in this case, and the 3% we couldn't identify was mainly the reason that we did not have available observation for that. For example, they only had 2 activities, or they have the activities in 2 different countries or cities maybe. Then after we validated our algorithm, we moved on to evaluating our EPZ searching algorithm on top of the protected activities or the activities that was using EPZs. So we deployed our searching algorithm, and we, in the first case, we considered all the athletes that have more than one EPZ-enabled activity. And in this case, we could identify 84% of these athletes. And in the next phase, we considered only the athletes that have more than 3 EPZ-enabled activities. In this case, we could identify 95% of the athletes. So once we found out that this EPZ feature is not good enough, we need to have some mitigation strategies. So we proposed 3 mitigation strategies to solve this problem or to improve this EPZ feature. The first one is the modify radius size. So in this case, we try to change the size of the radius to see its effect on our identification rate. In the second case, fuzzing EPZ intersection point, we try to remove some of the endpoint GPS coordinates and then see the identification rate. And then lastly, we use spatial clocking mechanism. But since the spatial clocking was more promising, I'm just going to go over the spatial clocking mechanism while you can go look the details of other 2 mechanisms in our paper. So spatial clocking is an adaptation of geo-indistinguishability in the context of fitness tracking services. What it simply does is it shifts the center of the EPZ or shift the protected location inside the EPZ zone. Now the likelihood of the protected location could be anywhere in the circle. Now, once we devised this algorithm, we tried to attack these mitigation strategies. So we use a very simple interpolation attack where we try to interpolate the directions of the route as they enter into the EPZ. So once we interpolate, we get all the intersection points. Then we select a group of intersection points and get their centroid. And we say our prediction is successful if the centroid is 50 meters in the distance of the protected location. We found out that even this simple interpolation attack works 45% of the time. And this spatial clocking mechanism still leaks the information, which shows you the natural tension that exists between concealing your activity while also maintaining the privacy. So once we have these mitigation strategies and we found this vulnerability, we contacted all the 3 fitness tracking applications that was using this feature. And we also told them our mitigation strategies, and all these 3 applications or services acknowledged our vulnerability, the vulnerability that we found, and deployed our mitigation strategies in one form and another. For example, Strava now uses our spatial clocking mechanism, where you can see that it randomly selects the protected location in the EPZ rather than the center that it was doing before. So once we are done with this, so what are the main takeaways from this study that we showed? So we showed that this EPZ mechanism, this legacy EPZ mechanism, was a bad measure from its infancy. We proposed some mitigation strategies, but there is still an intrinsic risk in sharing your information to the public. We advise users or athletes who use these services so that they should take extra measures, such as using private activities, making your activity as private, or do not share your activity that happened in an isolated area. Last point, we still need to find efficient and as well as usable privacy features that could be applied in the fitness tracking domain. Thank you so much, and I'm happy to take any questions.
Hi, so Yang Zhang from CISPA Germany. So one question is that, so have you ever make any in-depth analysis of your prediction result? If I assume that if you start your running in a park, it should be much less sensitive if you start running from your home. So have you ever seen whether your result is better on this not that sensitive location compared to the places where the privacy is really important?
Well, the place, I don't think so. The place matters when we run our algorithm. If I try to hide my location, if I'm in a very populated city or if I'm in an isolated place, I don't think so it matters. It will still find the center point and identify the protected location.
Okay, thanks.
Yeah.
So in your third defense mechanism, when you are finding the intersections of lines and you have already applied the spatial correction,
right.
You are assuming that the lines are straight, but it's not always the case because a user can take a curved path.
Right.
So did you consider anything on that?
No, we did not. We did not consider anything like that. But we just take the slope where when they enter into the they enter into the EPZ. Yeah.
Yeah. Then there may be some error in that. Maybe.
Yeah. So, but yeah, that's true. But we validated, and that's why it works 45% of the time, and it doesn't work for 55% of the time. Yeah.
Hi, I'm Sina Benson from University of Erlangen in Germany. I wonder if these fitness companies also publish things like speed with which the user is running, because actually I think it's meant to, to compare and to benchmark your own fitness against fitness of other users.
Right.
Do they?
Yeah.
So if you know the speed of a user, I wonder if it's possible, to approximate the location inside this circle, even if it's randomized.
That's an interesting point. But But we never considered this point. Yeah. Thank you very much for the comment.
You're welcome.
I have never used one of those applications, so my question may be naive. My name is Yalin Yang. I'm from Virginia Tech. So I wonder why the fitness company has to publish the real route. Is it possible that they can map the real route to a virtual world, like they create a virtual world and then there's mountains, etc. So they just map that real route to a similar route in the virtual world where they can put the destination and starting point from anywhere. It won't affect the data.
Right. That's a very interesting point. But usually the case is that you want to, you publish your routes to compete with other people. You want to brag about I run for 10 miles in this zone.
But in that virtual world, you can
that
brag,
virtual world, that
from
would be
Mount
awesome.
Everest too. That there is more privacy in that, but you can still compete with your other peers.
I have to say that this is a really interesting point. Yeah, if we can create that virtual world.
Okay, thank you.
Thanks.
Hi, I'm Stefan Soroyo from Microsoft Research. So that was a very interesting question. So I'm wondering, can you characterize what an ideal solution to your problem would be like? What are the properties that you want the perfect solution to have for the problem you're trying to actually characterize here?
Right. That's a good question. So the problem is that you want to publish your route, and you still want that people don't see your sensitive location. But as soon as you try to hide some part of it, but you still show some part of it, but people can actually guess from that part that you showed the hidden part. So the best solution will be that you take the whole route and map it to some other point in your map or somewhere else. But we still need to, that's an open question right now. We don't know what is the right solution.
Right, but it's difficult. So it's difficult to sort of evaluate this erosion of privacy when we don't understand what exactly we're aiming for, right?
Right. That's a good point. Yeah, thanks.
Hi, thanks for the talk. I wanted to raise the question of whether the endpoint is really more sensitive than the rest of the route. On the one hand, I understand the point that it might be your home, but say that it is your home, it has a lock on the door, and maybe you'd be able to figure out that address anyways. I would be a little bit more worried about somebody maybe hanging out in the woods in an area like where I'm running past, once every couple weeks, and nobody else is around. So I'm just curious what your thoughts are on the sensitivity of the rest of the route and not just the endpoint.
Sorry, I don't get where you're getting at.
So to clarify,
yeah.
You were focused, or the companies that are providing this endpoint protection are supposing that the endpoint is the most sensitive area on this route.
Right.
But I guess what I'm saying is that maybe the rest of the route is actually more sensitive because you might be running through a remote location where you're less safe. Right.
But this features also removes that part of the route too, right?
Well, in the examples that you showed, it looked like it was...
it was the sensitive, yes. That's an interesting point, yeah. But on top of my head, I have no answer for that.
Okay.
But yeah, that's an interesting thing.
Thank you.
All right, so let's thank Wajih once more for his wonderful talk and the questions.